the ritual of having to ask your names, and what you do. Know ourselves better. So the course is on deep learning. It's the buzzword in internet today. People talk about deep learning, machine learning, and all that stuff. So what we are trying to demystify the concept. It's not as complicated as people think. It's probably something you write multiplications and function transformations here and there, and then you're good to go. Outcome today is to understand basically the history of artificial intelligence and deep learning, to understand programming and machine learning. Well, those first two, I'm sure you probably would have. Okay, so my focus is actually in deep learning. Okay, so we're going to differentiate traditional machine learning models. Okay, as we progress in this course, there will be throwing at you here and there stuff like GPUs, TPUs, and the rest. So we're going to be as hands-on as possible. Also understand the workflow. So this is the first. Okay, we may maybe train a few models here and there, but it's basically about the basis. Concept about machine learning, and maybe most of the almost so you're just going to provide to fill in. At least that's what I hope to do. It's not good. It's not connected. not connected. All right, so this class will talk about, we said, okay. Or you can go the machine learning route where you collect data, okay, and pattern from the data you've collected, okay, with the goal that the machine can now use those patterns to replicate the intelligence within the patterns. Okay, so that's machine learning. Okay, the study of algorithms that learn from examples, experience, instead of relying on hard-coded rules and making predictions on the data. We've seen this in the last class. And I gave this picture just to give you the motivation of what we're trying to do. Okay, so this is a caricature picture, so you have to know that. Okay, so what you see here is just some procedure for making that beautiful, nice dish there. Okay, usually what you do, get inputs. Okay, what are your inputs? All the ingredients. Okay, now you know in your head, in your brain, that to make that food, you first cut the vegetables, season the chicken, and stuff like that. Okay, so if this was a computer, all right, you will have to program the rules. Okay, so the first thing you need to do is cut the vegetables, season the chicken, preheat the oven, and do all the stuff, and then the output comes the chicken. Okay, you also agree with me that there are also different techniques to make that chicken. Yes, this is not a one hard rule for making that. Okay, there are different techniques. So other people will come with this, but the output is the same. Okay, this is some classical way of representing intelligence. If you're going to give it some rules, okay, that will mix the input together and give us some outputs. Classical programming. Okay, machine learning is different. Okay? We learn from data. We will not tell the machine the rules because we cannot capture all the possible rules. I just said it. If you go back to this example, you'd see that a different person may come and say, okay, well, the person I want to do is preheat the oven. You know, I mean, there are different combinations. Okay? So, for certain problems, it is actually very difficult to hard code these rules. Okay? Think about it. How do you hard code if you want to make a computer program that will look at people and identify who is who? How do you do that? Using if. Okay, if, and you say if the eye is, curved a bit. I mean, it's very difficult, yes? There are so many combinations to play with. Okay, so for those kind of, okay, but allow the machine figure out the rules. Okay, so here our inputs still remain the same. Okay, but we now show it the output. In fact, we supervise the way the machine learns by giving it outputs. Okay, we tell it, okay, this is how you, this is the input, figure out the rest. Okay, so the machine or the program has this, complex relationship. Okay, complex map between, is the task of the machine to do that. Okay, but in this, something like this. Okay, so it means there is some relationship between the input and the output that we have to, okay, all right, and we'll allow the system to figure out the rules. Is this clear? Okay, this is where we are, and this is what I'm sure you've taken a course on machine learning. This is what you've been doing. Decision trees, linear regression, and all that. This is the holy grail. Random forest is a particular map, particular technique. Is it a map? Probably not. It's a particular technique. Okay. Okay, logistic regression. There are also techniques for doing this. To learn patterns. That's the goal. Okay. I mentioned linear regression. I mentioned, this. Okay. All right. So now we want to specify for pattern recognition. Taking out linear regression. So, okay, we want linear regression in, the deep learning in depth. Okay, to try to understand how we can actually use that to solve. So, what is deep learning? So, I gave this very high-powered definition. Some of you probably not used to, but we'll break them down as well. So, a type of machine learning technique, okay, focused on successive layers of increasingly meaningful representation. Definition that you hear when somebody gives you this kind of definition in public, but what we're actually trying to do is, okay, we'll get the data, we'll transform it to a form to another form, okay, and that other form to another form until it's between the patterns, okay, and then we can classify or do whatever we want to do with it. Different transformation, okay, you will see that as we continue. Simple matrix multiplications, okay, that two matrices together, or you multiply a matrix and a vector. These are the things. Okay? So we'll still come back here to this era of deep learning. There's a history behind it. Remember I said, well, we defined knowledge, yes, in machine. Now think about the humans are, and you want to build a computer program that behaves and use it to solve problems. Okay, and that's the history behind where we are today. Okay, we can also argue that this thing is gone off. It can also be argued if that right now with the kind of deep learning research that we have, it is nowhere near the way the human brain works, but at least it was an inspiration to get us where we are today. Okay, so this diagram, should I call it a Venn diagram? Probably. Just gives the scope of our discussion. We started with artificial intelligence. We want to build smarter programs. We want to build smarter machines. We want robots to replace human beings. Just kidding. Okay? And then we realize that we may not be able to program complex patterns. Okay? Instead, we decide to represent patterns, learn patterns from data. That's machine learning. Okay? And this also gave rise to so many techniques. Okay? But we realized that one way to do this thing effectively is to use neural networks. Okay? We didn't stop there. We said, okay, maybe we can get a deeper representation of data than deep learning. Okay? So this is like an overview of where we are today. Okay? But if you go back to the history, like I said, how do we get here? Last week, I was saying that if you are a scientist and you want to build you build a machine that will replicate human intelligence, the first thing you want to look at is the brain. So back in those days, in the 18th century and the early 19th century, there were no computers. Okay? So how do we achieve this? You can imagine how people were thinking back in those days. Where you ask yourself, where was Africa at that time? Maybe we were thinking in a different light. Anyway, the point is, at that point, people were saying to themselves, okay, if we're going to make a machine that behaves like a human being, we have to, first of all, study the brain. Okay? And as at that time, there were not much tools to understand what happened in the brain, or what happens in the brain. Until the development of microscope, microscope. Okay? So with the microscope, people can now see tiny stuff, things that they could never see before. They wouldn't have been able to see before. So somebody said, okay, well, maybe we can use that to understand the structure of the brain. Okay? And there came this diagram. Okay? A portion of the brain cell where it was examined under the microscope. And this guy drew this diagram. Okay? Santiago Ramon Cajal. This was as far back as 1906. Okay? But it gave a lot of insights to mathematicians. Because if you look at this diagram, you see these are like cells. Okay. Okay. All right. So this guy came up with an image, okay, of what constitutes what we know as the brain cells. This is biology, okay? But that gave a lot of insight. They found out that each of these cells they are sort of interconnected. So perhaps there's some sort of information interchange, okay, between the brain cells. That was a breakthrough. And of course, mathematicians looked at this and said, okay, maybe we can, come up with a mathematical model that represents a particular neuron. Okay, so each of these are called neurons. A particular neuron, okay, and we now have connectivity as it stands today. Okay, so each of these brain cells, you can model it as, a mathematical object. Okay, think about it this way. So this is a cell. It collects information from this guy, from this guy, and from this guy, and somehow from this other guy. Okay? So you can think of this region as aggregating information. So if signal comes from every other part, you can either sum it up, do some stuff, and then fire your own signal out. Does that make sense? Okay? That's led to its perceptron model. Okay? Everything is just been reduced to a simple mathematical operation. Okay? Where think of each of these lines, okay, as those signals that come together. You can either sum it up, okay, and put a squashing function to send out one output. This also goes to another cell, okay, sums up, squashes another output, and so on and so forth. So you don't have a network of information. This can now be used to model that. Does that make sense? Okay. In this case, each of these x1, x2, x3, up to xn, they are the inputs. Okay? All right? If we want to enable learning, we can now say for each of the inputs, or in this case, they call input features, okay, we can include another variable, okay, that gives each input an importance. We call them weights. Okay? How important is x1? Is represented by wij. Okay? How important is x2 is represented by w2ij, and so on and so forth. Are you following? So that if you now multiply these two together, squash the sum, put it through maybe some threshold, you can get a single output for each neuron. Okay? So what does that tell you? It means that for each of these inputs, x1 and up to xn, they are fixed. Okay? If I want to learn, it's like adjusting a meter. Okay? I'll just adjust how important xij is, how important x2j is, and so on and so on. I'll just tune them up, okay, to give a certain output, a certain pattern. Does that make sense? Okay? And that's the whole idea of the artificial intelligence. All right? If you set up a network of these kind of structures, your goal will now be, let's tune those weights, let's change the values, okay? If you tune it very well, then it will meet a particular task. It will be able to do a particular task. Okay? Now, this is not complicated. It's just simple vector multiplication as it stands with the perceptron network. Okay? So this was done by this guy, and they even went ahead to propose something called the perceptron learning algorithm. This was in 1943. There were no computers at that time. It was all, some conceptual thing you do on pen and paper. Okay? Now, the first person to actualize this concept, okay, remember I said that there were no physical computers that we had, was Frank Rosenblatt. Okay? So he took this concept. I don't know if he was an engineer or something. He's an engineer, or I don't know. I'm not so sure. You have to look it up. Okay? He replicated this thing, okay, as a hardware. So those connections are represented by wires, there are transistors, there are resistors. He put that thing together, okay, to form the perceptron machine. And then, of course, the media at that time hyped it up. We've now found a way to represent human knowledge in machine. Now, machine can now work and behave like humans and stuff like that, So this is more or less like the birthplace of the artificial intelligence, artificial neural network. Any questions about this? We have gone far away from this concept, okay? We are now in the era where we can now we can do a lot of things with this kind of setup, okay? We can put them together in different forms. They're called architectures, okay? To learn a particular task. But the essential thing is we have neurons, okay? And each of those neurons receives connections from, every other neurons, and each of those connections are weighted, or is weighted, okay? You sum up the connections and you fire out an output, okay? This is a single artificial neural model, okay? So like I said, a lot has happened since then. Now we are in the era of very large models, ChatGPT, I'm sure you've heard about it, okay? A lot of these concepts essentially boils down to matrix multiplication, transformations, and all that. Because if you go back to this, okay, this is simply multiplying two vectors together, okay, the dot product of two vectors, and then you pass the output through a nonlinear function. That's all. Just one line of code, one line of statements, okay? But now we've gone a lot more advanced, okay? We can now put these things up, set up different kind of transformations to come up with some complex architecture that we can use to solve different problems. And we'll be looking at those ones as we continue. Okay, so like I said, the perceptron is very, very simple statement. In fact, this whole thing here is what you see as your output. Okay? These are the weights. Remember I told you, we give importance to every feature. Okay, every input feature. Okay? So W0 is how important 1 is. W1 is how important X1 is. Okay? And our goal will be, how do we change this, this configuration to match a particular output? Okay? And that's the learning. Okay? That way we can now encode those rules that I talked about. Okay? And those rules can be encoded in this vector. Okay? So if you have this input plus this vector, you multiply both of them, the dot product of the two. The output, you pass it through a nonlinear function. You get an output of a single neuron. Is this clear? Okay? What if you now want to have plenty neurons? Okay? It's still the same thing, but slightly different. Okay? Now, this is one neuron. This is another neuron. Okay? All in one layer. All right? These are the inputs again. X1 up to X4. Okay? But this guy is going to weight every one of these inputs. This is going to weight every one of these inputs. We can collect all these weights now as a matrix. Okay? Represented by this. Are you following? Okay? All right? Now, when you use that matrix to multiply this, you're going to get a vector, isn't it? A vector of output. All right? But the dimension of this matrix will determine whether you get a vector or you get a scalar value. Like in this case, in this diagram, okay? We want a situation where we have a matrix, okay, multiplying a vector. Okay? What do you think the dimension of this will be? Okay? That is, you have a matrix multiplying a vector. Okay? You get a single output. If you don't understand, don't worry. Maybe I'll ask that question much later. But the idea, like I said, is we can now connect all these arrows, okay, into a large matrix. Are you following? Okay? Still do the same multiplication like we did in the previous case. Okay? But this is now a matrix. All right? Still squash it through a nonlinear function to get an output. Is this clear? This line of code is this diagram. Is this clear? Okay? So if we want to learn, what we'll do is, this is like a variable now, our variable. We'll just be adjusting the content of this guy so that it will match a particular output. Are you following? Okay? And once it matches that output, we'll say that the system has learned whatever representation that we want it to learn. Okay? Now, this is the artificial neural network. Okay? This structure. Then what is deep learning? This is deep learning. Okay? Taking this kind of arrangement to a whole new level. Okay? Now, remember, we have only the inputs and some layer and then final output. If you now go as deep and deep and deep and you're doing deep learning, it's as simple as that. Okay? So what does that tell you? It means this is the first input. Okay? These arrows here, they are represented by a matrix W. Okay, so the first matrix, let's call it W1, which is this guy. Okay? You squash it, get one output, okay? Multiply it with the inner matrix here. Let's call it W2. Okay? You squash it, that gives you the output coming back out of this guy. You multiply it with another matrix again. All right? So you can decide to put as many layers as possible. Okay? The entire thing is represented by this nasty looking line of equation. Any questions? Okay? So it now depends on how you want to do this matrix multiplication. Okay? So this is where your creativity now comes in. You can say, okay, maybe I want to multiply maybe a small subset of the input. That's convolutions. Okay? Maybe I want to do some fancy slashing, and that depends on how well you set up this multiplication. So my argument here is what you see here, the standard operation that goes on at the background is matrix multiplying another matrix, or matrix multiplying another vector. Is this clear? Okay? And this, ladies and gentlemen, is deep learning. Okay? Now you agree with me that we have caused problems for ourselves. Okay? It was easy to just look at this setup and just adjust the weight to get an output, yes? Yeah? But now we have layers and layers and layers of this setup to tune. Okay? How do we do it? We can't do it by hand. We can't. We have to find better ways that will give us a way to adjust this weight that we are talking about. Okay? So the most part of this class is how to do that. It's not just to set up the deep learning network. Okay? But if we've set it up, how do we just change those parameters, okay, so that we can get the model to learn a particular pattern, the pattern that we want. Okay? Is this clear? And I also argue that for some of you who maybe did sciences, you have actually seen something like that before. It's called gradient descent. Okay? It's called taking a derivative of a function and setting it to 0 if you're doing a closed form solution. There are things that you already know, okay? But we now want to represent them in a form that we can actually get a computer to do it, okay? And learn, these weights that we care about. Any questions so far? So this is the major, excuse me. So for the most part of this course, these are the type of stuff we'll be playing around with, okay? We'll be looking at these kind of, setup, and we want to ask ourselves, how do we train a model like this? Okay? These are the kind of questions we'll be asking. We also want to ask ourselves, how large is this representation? How do we determine how many parameters we are going to be changing? Okay? Currently, the likes of the large language models, the number of parameters you have, they are running into billions, meaning there are billion variables that you have to tune to learn something. Of course, you can't do that by hand, okay? There are algorithms for doing that, these things, and we're going to talk about these algorithms. Okay, so that's more like an introduction of what deep learning is all about, okay? It's just basically those layers and layers of artificial networks, okay? Or you can think of it as several function transformations, compositions, several compositions and function transformations, which goes back to this definition that I talked about. Okay? It's a subfield of machine learning where data representation are successive layers. So if you go back to this diagram, you see that this is my first data, okay? I transformed it by multiplying it with the weights into another form, okay? I now have a new input, all right? That also I transformed, okay? So this is my first layer, all right? Are you following? The second layer is a transformation of the first layer, okay? The third layer is a transformation of the second layer, and so on and so forth. This is deep learning, okay? All right? The easiest part is doing this, okay? The most difficult part is how do you actually learn? How do you actually tune those weights, okay? Is this clear? All right, so one of the tools that we're going to be using to, to do this stuff is PyTorch, okay? PyTorch is a framework. I think of it as a library, okay? That has been built to help us easily do some of these things, okay? Like I said, one way to tune these weights is to calculate the gradients of this function, okay? I'm sure when the moment I had gradients, some of you, that thing we did in secondary school, in university, that was problematic. We may not necessarily have to write down the gradient of a function by hand because we cannot even do it, okay? Think about it. Imagine you have to write a gradient for this function. It's complex, okay? Machine learning library, okay? It was actually originally designed and used within Facebook, okay, which is now Meta. But later they released it for public use. It is flexible, okay, and has support for computational graph, which is essentially a tool for computing those gradients that I just talked about, okay? So the idea is whenever you make, whenever you have a computation, okay, like you multiply two matrices together, okay, it makes a graph, a dynamic, keeps a record of all the computation that you've done, okay, with the hope that if you need to take the gradient of whatever computation you've done, you can easily do that easily. That happens at the background, okay, and that is why one of the reasons why we can do most of the learning that we have today, just because of this computational graph, which is why I colored it in red. You can write very fast deep learning code in Python. You can do that in a few minutes, okay? So you can set up this in a few minutes and train it, okay? With the help of this framework. Okay. And there are a whole stack of, pre-processing libraries. Usually, remember we're talking about machine learning. So when you get the data, you have to pre-process it, okay? There are lots of tools, functions, methods that you can, just grab from the PyTorch suite to do most of this pre-processing that we are going to be looking at. Is PyTorch the only library? The answer is no. There are lots of them, okay? You can look at the ones that I've listed. There's TensorFlow, there's Keras, but now you have Keras TensorFlow almost merged together, okay? There is Café, there's MXNet, there's Tiano, there's Chain, there are many, okay? The reason why we're using PyTorch is because it is favored by the community. There is more support. If you run into problems, you're likely to get a solution in PyTorch, okay, than in any of these other frameworks. And of course, it is Pythonic, meaning if you're the type that is used to writing object-oriented kind of programs, then of course PyTorch is your go-to framework. Okay, so this graph shows the trend in the usage of PyTorch over the years. You can basically read through. 75% of people now use PyTorch as a framework for their deep learning based project. And this image is obtained from paper with code. By the way, you can always go to paper with code to get, if for example, you've seen a fancy project that you like, okay, and the project, okay, and if the project has some, the source code, you can always get both the paper, the description of the project, and the source code from this site. That's why it's called paper with code, okay, and run it and try your hands on the new project. Okay, so having said that, most times when we talk about deep learning projects, we always talk about GPUs and TPUs. Okay, what do these things mean? Now, usually when you're doing matrix multiplication, matrix vector multiplication, matrix multiplication, it's heavy computation. Okay, so much so that if you do this computation on your normal laptop processor, it may not be fast enough to achieve what you want. Okay, so people realize that the GPUs, which were initially made for games, okay, GPU accelerators for games, can also be used, well, if you think about it, games use their heavy computations that will run in the background. So instead of doing these your multiplications and stuff on your processor, you can actually move this computation to your GPUs. Okay, all right. So GPUs are basically graphic processing units that are now used to run these deep learning based projects. Okay, and afterwards the TPUs were developed, which are now specifically purposed for manipulating tensors. What are tensors? Tensors are just arrays, multi-dimensional arrays. Okay? Like in the case of the weights that you saw here, this is the tensor. Are you following? Okay? All right, so you can have these tensors in multiple dimensions, n-dimensional tensors. Okay? So these are hardware devices that have been, the TPUs are hardware devices that have been optimized for tensor operations. What are these operations? Like I said, matrix multiplication. Okay? All right, matrix addition, subtraction, matrix scalar division, all these things, they've been optimized, these TPUs have been optimized specifically for them. Any questions so far? Okay? Is that? Yes. Tensors are just other names for matrix. They are actually multi-dimensional arrays. Okay? That's just what they are. Okay? So the idea is, so we now encapsulate, we now call them tensor objects because we can now perform operations on them. Okay? Like addition, subtraction, multiplication, and the likes. Okay? So we can have a tensor, all right, and we decide we want to do the addition and multiplication on our CPU, which is not really advisable, okay? Because these are heavy multiplications, all right? Think of multiplying a million dimension by a million dimension matrix. That's a lot, okay? You may decide you want to move that kind of computation to a GPU or a TPU. The idea is because this computation can now be done in the GPU in parallel, okay, and a lot faster. So that speeds up. So tensors, they are multidimensional arrays. They serve as the fundamental structures for representing data in any deep learning project. Okay? Every data you collect, you have to represent them as tensors. More specifically, numbers, arrays of numbers. Okay? If I want to do a project involving speech recognition, for example, sounds, okay? I have to find a way to convert my sounds to multi-dimensional array of numbers, before I can, because we are doing, mind you, we're talking about matrix multiplication here, okay? Can you multiply alphabets? No. So you have to represent every data point as numbers, okay? As some tensor, all right, before you do any computation. So they are the fundamental data structure of representing any kind of data. So in machine learning, everything gets converted into numbers, and they are stored as tensors before you feed it into a model. Questions? Yeah.
So you You said you had to convert alphabet into numbers.
Yes.
You mentioned you use like one hot encoding, binary encoding, and debug encoding. Is it the same thing you're going to do with
That's a good question. Yes, for categorical data, you do that. Let's say you're working on a survey, okay, where you collected names of male, female, okay, or states where people stay, and they type those things in alphabets, okay. You convert those to numbers, okay. What if it's an image? Well, I can just give you an example. Sound, okay. Sound is represented as a waveform, okay. You have to find a way to convert the sound to numbers. Essentially everything, okay. Video, you convert to numbers, okay. So yes, one hot encoding is one of such conversion, okay. But there are lots of other conversion, and the one hot encode is suited for those kind of ordinal kind of data, where you just want to get the categories and represent them as a series of either zeros and ones. So you're still saying the same thing. That representation you get afterwards is a tensor. Do you understand? Whenever you've converted it, once it gets to zeros array form, you think of that as an array of numbers. Think of that as a tensor. Okay? It may not necessarily be binary. It could be anything, any number. Okay? It could be negative, it could be positive, but the moment you've converted the whole thing and you represent it as an array, okay, then you're dealing with tensors. Although it can be argued that in a tensor you can put other data types, but what the data type you care about is actually the numbers, because you cannot perform arithmetic operations on non-numeric data. Okay, so we want to represent our data as numeric form in a multi-dimensional array, which are tensors, and then we can perform operations. Okay. Any other questions? Okay. Remember I said tensors are multi-dimensional array. These are tensors. Okay. Your input is going to be represented as a tensor of numbers. Okay. The weights also, those things that you're going to tune, those W's, they are also going to be represented as array of numbers. So these are tensors. Okay. So in the example that I gave, if we're going to build some hypothetical cooking algorithm, machine learning algorithm, the ingredients will be represented as a multi-dimensional array of tensors. Okay? All right? The weights, these neurons, they are also going to be represented as multi-dimensional arrays. The output would also be represented as multi-dimensional arrays. So everything reduces numbers. Okay? So this is the deeper representation of these tensors. Remember I said they are multi-dimensional array. Okay? So what you see here is a tensor in PyTorch. Okay? So this is the point where I think I can write on the screen. Okay? Now, this tensor has a dimension 1 by 3 by 3. What do we mean by that? Okay? It's like stacking up matrices. Okay? The first dimension is represented by this square bracket. Okay? Let me see if I can. Okay? All right. So if you have a tensor, the outer bracket, that's the dimension 0. Okay? Are you following? Yes. All right? Yes. Okay? The second dimension, which is dimension 1, okay, will be represented by the next inner bracket. Okay? All right? The third dimension, which is dimension 2. This is very important because it will help you understand the multiplication we are going to be doing. Okay? The third dimension, as you guess, will be represented by. Are you following? Yes. Okay? Now, if in these third dimensions you have 3 numbers, okay? All right. Then in this third dimension, the shape is 3. Are you following? Is this clear?
First, second, and third of the first dimension.
Yeah. So this is dimension 0. Start counting in 0. Okay. This one is dimension, and this one is dimension
3.
Okay. All right. So anything inside this, okay, is the shape of this dimension. So how many objects do we have here? No. Within this, assume that this is only one entity. Okay. You only have one thing inside dimension 1. Okay. All right. If I want to put 2 things in dimension 1, I'll put command here, and I'll put maybe 4, 2, 1. Are you following? Okay? It means in dimension 1, there are 2 objects. Okay? Each of those objects is of size 3. Does that make sense? This is very important. Who's confused? Let me start all over again. Yeah. It's a multi-dimensional array. Okay? The typical array that you know of. Okay? The typical array that you know of is something like this. Okay, so let's represent this now. Okay? Let's say this is a matrix of 3 by 3. 4, 2, 1, 2, 0, 2, 1, 2. Okay? If you're going to represent this as a tensor, all right? Are you following? We'll start with the first dimension. Okay? Which is essentially this guy. Okay? All right? And this one. And this one. So you're saying that in dimension 0, we have 3 items. Okay? What are these items? The first item, the second item, and the third item. Are you following? Okay? Now, in each of these items, are you following? You have what? No, in each you have 3. Okay? So this is 4, 2, 1. And this is 2, 2, and this is 1. Okay? But we are going to be dealing with a lot more complex representation than this. Are you following? Okay? You're going to be dealing with n-dimensional tensors. Okay? Which is why this is giving us an example. This is not as simple as this. Okay? Just like we said, in 0 dimension, there are how many items? 3. Okay? All right, so I can write the shape of this thing as the first dimension. Okay? So let me know. Okay? The first dimension is only one item. Okay? All right? In the second dimension, how many items do we have? 3. Is it 3? Oh, it's 1, sorry. In this 0 dimension, there's how many items? 1. Okay? Sorry, in this 1 dimension, how many items? 3. Yes, correct. Okay? All right? And in each of these dimensions, how many items do we have? 3. Does it make sense? Okay? Is this clear? So in this case, this is dim 0. Okay? This is dim 1. Okay? And this is dim what? Okay? The number of items in dim 1 is this. Okay? The number of items in dim 2, 1, 2, 3. Okay? The number of items in dim 3, scalar values, 1, 2, 3. So the shape of this thing is 1 by 3 by 3. Does that make sense? Is this clear? This is central to what we're going to be doing. Okay? Because if you multiply two matrices together, you can multiply them based on a particular dimension. Okay? You can say you're multiplying them from the second dimension. Okay? If you add two matrices together, you might add them based on a particular dimension. Okay? And if you recall back in your school days, the dimension of the object you add must follow certain rules, which we're going to see in a moment. Any questions? So going back to start, you now understand what we mean by this. Okay? The entire thing is called a tensor. All right? Okay? The first bracket indicates the dimension, the zero dimension. Second bracket indicates the first dimension. The third bracket indicates fourth dimension. Okay? So if you go by this same analogy, in the first bracket, how many items do we have? One. Okay? In the second bracket, how many items do we have? Three. This one, this one, this one. Okay? In the third bracket, how many items do we have? Three. So that means the shape of this tensor is 1 by 3 by 3. Is this clear? Okay? Once we have the tensor, there are many things, just like I said, multiplications. A lot of multiplications, a lot of additions, and stuff. Okay? To multiply two matrices together, if you recall from high school, you get the roll of the first one, okay? Multiply by the column of the second one. You're not going to do this thing by hand. Maybe you might do it in your quiz, but to compute matrix multiplication in PyTorch, you just type this. See this command, this function, torch.matemore. Okay, you put the first matrix, comma, you put the second matrix. That's all. Okay, that's why it makes it a lot easier for you to write this kind of, to build this kind of models. Okay, train this kind of models without sweating. Okay, because these libraries have been made available. Okay, so this is another example. This is a matrix of 3 by 3 multiplied by also 3 by 3. Okay, this is a matrix of, yeah, basically. Okay, one rule for multiplication that we were taught in school is that the dimension must be of a certain form before we can perform matrix multiplication. And that is what I put in red. Okay, if you're multiplying two tensors, okay, the last dimension, this shape of the last dimension must match the first dimension of the second matrix. 3, 3. Is this clear? Otherwise, it will be an error. It's on the, okay? So you cannot multiply a 3 by 3 by a 4 by 2. Are you following? Okay? So let me go to, so what we're saying is, okay, if you have a tensor of dimension 3 by 3, okay, and you want to multiply it with another tensor of dimension 4 by 2, this does not work. Okay? Why? Because the last dimension size and the first dimension size of the other matrix do not correspond. This is 3 and this is 4. So this is not possible. Okay? So for every, and I say this because when you are coding, you're going to be getting these kind of problems a lot. So if you don't know, you'll be wondering what exactly is the problem. Why is my code not running? Why is it not working? Okay. So you'll be wondering why it is not working. And that's simply because the dimensions of the tensors don't match. Is this clear? Okay. Let's No, edit. Okay, so let's continue until we find. Okay, so this is where we're talking. Okay, so the dimensions must match. Okay, more importantly, if you multiply two matrices together, okay, all right, so now let's say I have a well-defined matrix, 3 by, or tensor, let's call it tensor, 3 by 2 times 2 by 8. Okay? If you multiply these tensors, the dimensions match, yes? The final output, okay, of this tensor is going to give you a dimension of 3 by 8. This one will cancel out. Okay? Very important. Why am I saying this? Because you need to know the shape of the tensor of your output. Okay? Because you need it to feed into another output. Are you following? Okay? So if you define some weight configuration that we multiply with some input, you need to know the dimension of the output so that you can define, you can know what other matrix to multiply with that output. Does that make sense? Okay? So two things, the dimensions must be well defined. Okay? And then once you do the multiplication, the resultant dimension of the new matrix is going to be the dimension of the first, all right, times dimension of the last. What if you have a crazy tensor? Okay, like 1 by 3 by 4, okay, multiplying, you see where it goes beyond, okay, multiplying 4 by 2 by 1. Is this multiplication well defined? Yes, because it's too much. Okay? So the resultant tensor you're going to get is 1 by 3 by 2 by 1. Very important. Is this clear? Okay? So we're going to be doing a lot of these. In fact, this is what forms the basics of what we're going to be doing. Okay? All right? With this, we can understand the number of parameters we are going to be tuning. Okay? All right? Like in this case, the total number of parameters okay, is 1 times 3 times 4. All right? Okay? So if you multiply, if you do some linear transformation with this multiplication, the total number of parameters you're going to get eventually is 1 times 3 times 2 times 1. That's 6. Do you understand? This also defines the size of the model. Okay? So you hear that people say a large language model is 2 trillion parameters. They are basically talking about the weights of these models and how large they are. Okay, so we're going to talk about a lot of this, especially when we start looking at writing this basic Python code. Like I said, I'm going to give you most part of the code. Okay, all you need to do is just fill in the points that I think will be of most interest to you. Okay. So the next thing we are going to talk about is how to do some of these things in PyTorch. Okay, we are going to be using the Jupyter notebook that you already know and you already use. You can use that from your phone. Okay, all right, to do some of these basic, operations that we have just talked about, like maybe adding 2 tensors together, multiplying 2 tensors, subtracting 2 tensors, taking the dot product of a tensor, and doing basic operations, taking the inverse of a tensor and all this stuff. Okay? Any questions? Any questions? Okay, so you have to. So any questions? So who? Huh? Okay, what are the questions? Okay. I didn't forget the online students. I'm sorry. Okay, so okay. So what are the questions? Okay, but you should maybe curate them. Okay. I think the best to curate these questions. Is there like a forum for people to submit questions and stuff? Yeah, on Telegram. Okay. So if you can hear me, I think if you have any questions, maybe now is the time to ask, so that I can read them straight up and then explain. I think you can do that directly on live, I guess. Okay. So let me see if I can write on my screen. Okay. So we apologize for the break in transmission, I guess, for the online viewers. So hopefully we'll make better preparations next time and come up with ways so we can project both the board and okay. It says they missed out on the tensor explanation. Okay, cool. So let's see if I can use a notes part to explain. All right. So awesome. All right. So if you can see my screen, let me. Okay, fine. So if you look at, am I disconnected from the screen? No, I can't see the projection. All right. So if you look at, okay. Okay. So if you look at what we are trying to say, we said a tensor is a multi-dimensional array. Okay, that's essentially what they are. Okay, think of it as arrays stacked up upon arrays. So that constitutes the multi-dimension. So the example you see on the screen here, okay, is one of such example of multi-dimensional array. Okay, and how do you know the dimension of the array? You know the dimension of the array by the number of square brackets, okay, and the number of items within each square bracket. Okay, so if you look at the first square bracket, this one, okay, all right, assume that every item inside is one object. So you want to ask yourself, how many items are in the first dimension? Okay, so that's dimension 0. Okay, how many items have comma within that dimension? Okay, all right. So if you look at everything inside, there's only one item, there is no comma. Okay, that tells you that the dimension of the first curly bracket is 1. Are you following? Okay, if you move to the inner bracket, okay, that is dimension 2. So by indexing, it's actually dimension 1. Okay, are you following? Now look within that dimension. How many objects have commas there? 3. This is the first one, comma, the second one, comma, the third one. That tells you that dim 1 is of size 3. Are you following? Okay. If you now move to the third dimension, which is dim 2, okay, within dim 2, how many objects have commas inside? 3. Okay, that tells you that the shape of dim 2 is actually 3. Okay, and I think we are done. The rest are just closed brackets. Okay, so we're interested in the number of analyzing the number of opening brackets. Okay, so in general, we've seen that for this tensor, the shape is 1 by 3 by 3. Is this clear? Okay, and this will define how you do these multiplications. Okay, so we give an example here. Suppose you have 2 tensors. Okay, the first one is of dimension 3 and 3, that's 3 by 3. The second one is of dimension 3 by 2. This multiplication is well defined, okay, because the last dimension size is 3 for the first matrix, and the first dimension size is also 3. They must match. Okay, so if they match, it means that these 2 tensors can be multiplied. Okay, and if you multiply a 3 by 3 by a 3 by 2, okay, the resultant matrix is going to be 3, okay, by 2, meaning those dimensions that match will cancel out. Are you following? So if you look at this, diagram here, this is a 3 by 3. This is a 3 by 2. Okay, by the time we do the multiplication, those matched dimensions cancel out. What we get is 3 by 2. This is important because if we now go to n-dimensional tensors, okay, all right, this will determine the shape of the tensors after we have done the multiplication. Okay, so I gave an example. Let's see if I can write on this, but I don't think so. So let's see. Let me see if I can increase the font size for this. Okay, if you have 3 by 3 by 4, this is one tensor, okay? All right, you want to multiply it with another tensor, okay, of 4 by 3 by 2. Will it work? No. Okay? Because the last dimension of the first tensor is 4. Sorry, it will work. Okay? The last dimension of, yes. In fact, in my head, I think I wrote 3. I thought 3, but I wrote 4. Okay, it will work. The last dimension matches the first dimension of the other tensor. Okay? So the dimension of this afterwards will give you what output dimension? 3 by 4. Good. Okay? Is this clear? That's essentially what we're saying. Okay? Because for most time, in most cases, you are going to be multiplying tensors. You're going to be adding tensors. If you add the tensors, the dimensions would match. The dimensions should match, so there's no cancelling out. But multiplication is very key. Okay? Because the match dimension will cancel out. That is what we're trying to say. Okay? And like I said, finally, we're going to see how these things really take shape, okay? When we look at the Colab notebook and maybe do 1 or 2 of these operations, additions, subtractions, okay? And possibly build maybe a simple feed-forward neural network to explain this concept. I think that should be all for now. Any questions? Any questions? All right, so as always, it's nice meeting you guys. Hopefully we'll have more fun in the next class. Thank you.
Which is the attendance?